everyone. Yeah, excited to be here.
Yeah.
Should I use
microphone? Microphone is better.
Yeah. Hello, hello. Okay. Yeah, excited to be here. Probably my first JSConf. I will only have JavaScript on my slides that will offend you. So what I will show you today is a bit of a whirlwind tour through V8, through the optimization pipeline that we currently have in V8 for the Chrome browser. Yeah, let's get started. My clicker is not working. Perfect. It's technical issues. It's maybe now the clicker is working. Now the clicker is working. All right, so let's get started. Here I have opened a website. And I have actually opened a website with this really nice tool that I can highly recommend you try out. It's called Crossbench. And what I can do with it is it has a bunch of different modes. But here, for example, I can say load a web page. So this is this load predicate. And then I can tell it, so I can do this in multiple browsers. And then I can tell it, please attach a probe. In this case, I attached a Perfetto probe, pre-configured for V8. We don't need to go into the details. What it does is it kind of records what happens in the browser. And then I can show this nice graph of JavaScript events. Now, this is the main thread while loading this website. We start here at 0.5 seconds. Before, nothing happened. I guess network, DNS, who knows. And at the right end, we have something like first contentful paint, where the page is starting to do something. Now, already from this graph, there are a couple of interesting things. Like if you look at this thing here, there is like nothing is happening. What is going on there? So this is just the main thread. So let's look at what other threads are doing. I can filter for different event types. So for example, I filtered for this event type here, which is parse events. And now I have a big parse event here. Now we also know why nothing happened there. So presumably, we had a web page. The web page maybe looked like this, right? It had like some HTML around. In the middle, there was some JavaScript. So Blink, the renderer, will get the web page. It will parse it, the HTML around. At some point, it will say, okay, now I need to do this JavaScript thing here in the middle. I can't continue. So at that point, Blink will take the JavaScript, hand it over to V8, and then we need to do something. And until we didn't do the something, this page cannot continue to load. So if we continue a bit further, and if I show you all the parse events, you can see two different kind of events. You can see the big blob, where we were blocking the main thread. And then you can see there's actually two of these blocking events. And then you can see like a bunch of interspersed tiny little events that are kind of concurrent to the execution of JavaScript. So what is going on with these? So let's look at how V8 parses JavaScript source code. I have another silly website that does the following. We have some event handler, and we have some error handler on this slide. And the first thing actually V8 does when it sees this, this code is it will identify function literals. So we'll scan through the file and see, like, are there any functions in there? And we'll not do much more than that at this point. We'll just remember which functions exist. And that's the blocking part. But then we can already start executing. And maybe the user clicks on something, this event fires. And now we actually need to do something because we need to execute it. So at this point, only at this point, we will start parsing it. And then maybe you can see here, there's an error handler. So let's say there's no error on this page. So we don't even need to parse that code. So this can just stay, like this can stay on disk. We never touch it. We don't even have to look at it. And you might say now, okay, does this make sense? We need to traverse the whole source code twice. It actually does make sense. Like many websites have huge amount of JavaScript that is just never used, that is never executed. So it's a bit of a random number. I don't have a good source, but there are websites out there where 80% is unused source code. There is something exciting that I want to mention, and there is a bit of heuristic going on. Sometimes we think, okay, here is a function that is certainly going to be needed to display like the first part of this website, so we'll parse it eagerly. And now there's a new feature where you can control this. So there's explicit compile hints. You can look at this blog post where basically you can say, you can tell V8 which parts of your JavaScript sources should be treated eagerly and not go through this deferred lazy recompilation. So what I will do throughout this talk is basically fill out this slide here. So this is a very high-level architecture of the whole optimization pipeline as it currently exists, or as it soon will exist in V8. And we're now here where we have gotten some source code from the network or from the cache, and it's in text format. We have already identified where the functions are, and now we need to actually parse one of these functions. So let's look at an example function. Again, a very silly function that takes the difference of two arguments and caps it at 0. It's just for illustrative purposes, and it fits on a slide. So the first thing any compiler does, and maybe now I'm boring people, maybe not, so this is a bit of a compiler construction lecture almost. So the first thing a compiler needs to do is actually figure out what is the structure in this text of the source. And one thing that needs to be done is we need to find identifiers, keywords, these kind of things. And so the structured representation that we internally use for this is called an abstract syntax tree. It basically represents what is this function doing in a structured form. It has all the bindings resolved, it knows what kind of variables there are in this function, and if we just go through it, we discover different statements, different expressions. They all turn into nodes in this graph. In the end, we have like this graph, which represents this whole function. And now we have a structured format that we can actually work with. We could execute this. So there are AST interpreters, which is basically an interpreter which takes such a graph of a function and just execute it. So it's not hard to envision. You write a visitor that goes to every node, computes what it does, and in the end you get a result. The only thing you need here is basically the values for A and B, and then you can run this function. This is not what we do, because that would be extremely slow. So the next thing we need to do with this AST is to turn it into bytecode, which is essentially a dense format of this AST. So this is the first step, and this will bring us to the first executable format that we have in the pipeline. So the bytecode is just a compression of this AST in that sense. So let's do it. Let's go step by step. We visit this tree from left to right, let's say, and we arrive at our first bytecode. So this bytecode loads the argument A1. So A1 is is argument number 1, not the first argument. The first argument is the 0th argument. So it loads argument number 1 into the accumulator. What is the accumulator? It's just some implicit register that the bytecode interpreter has. And you see here, like all these bytecodes, they are basically written in a way that they're as dense as possible. So I don't need to say where this goes to. It's implicit. It goes into the accumulator. Subtraction, for example, has 2 implicit inputs. So it says subtract argument 0, but the other operand comes from the accumulator, and the result also goes into the accumulator. So again, super dense format. Yeah, and so now we go through this. I don't actually have time to explain all of this, but you can imagine how it goes. So basically, we have bytecodes for the different kind of expressions that you have in JavaScript, and they all, they basically now, this is a quickly executable format. Now you can write an interpreter that dispatches on these bytecodes. For every bytecode, it has a piece of functionality that it implements. And now we can actually efficiently evaluate this function, and we can also efficiently store it to disk. We can efficiently keep it in memory. So this is the baseline format that we have for JavaScript files or functions. Now, this will actually not give us fast execution. So we actually have native compilers that produce machine code. And now you might think, like, why don't we just make everything fast? We might want the fastest version for every function. And what I've added here to the slide is basically all our optimization tiers. So the bytecode is the first tier. And now you can see compile events for all the later tiers. And you can see that tier 2, we're deploying relatively aggressively. Almost everything that gets executed will also end up being optimized by tier 2. But then tier 3 and 4 is much more selective, and especially if you look at how long it takes to compile a function in tier 4, sorry. If you take one of these blocks and then imagine that every one of the small blocks would be as large as this block, you can easily see how this website would take, like, I don't know, 2 minutes to load if we would compile everything with that compiler. So that's clearly impossible. You want your website to load in 2 seconds. That is roughly the budget that we have, right? So that's why we have this tiered compilation strategy, where we have a bytecode interpreter that is, like, basically the bytecode is designed that we can start running as quickly as possible. Then we have a first tier called Sparkplug, which does no optimizations mostly, and it's basically there to remove the interpretation overhead of the bytecode interpreter. And then we have 2 more optimizing tiers. One is called maglev, and the other one is currently called turbofan. And maglev is like the kind of fast-paced optimizer that we can deploy more liberally. And then finally, turbofan is the last tier that we only want to deploy selectively. Maybe if you have a function which really does a lot of heavy numerics or something like that, we'll use that compiler. Okay, so now we start with the first, sorry, I went a bit fast. So this is Sparkplug, the second tier that I want to talk about now. And this is the first native compiler. Again, I'm linking to a blog post that I can recommend that kind of goes into more detail. And in my architecture diagram, it goes in here. It's basically parallel to the interpreter. It does everything exactly the same like the interpreter would do it. This is the compiler. It fits on one slide. And it's a bit of a joke, but it's not far from the truth. So what the compiler does is it just goes through every bytecode linearly, and then for every bytecode emits what this bytecode would do in native code. So let's do this. I have more assembly than JavaScript on my slides. So this is the load argument bytecode in x64, x86, sorry. This is just a move instruction. The accumulator, that's a register on this architecture, so racks. And then in our calling convention, arguments to JavaScript functions come from the stack. So that's an access of the stack at a certain offset. So that's the translation of this bytecode. Nice. Now this bytecode is a bit more complicated, and I'm going to use a trick here. Because actually, I don't want to write down what this bytecode can do, because you all know that minus can do like tons of different things in JavaScript. So what we do instead here is we just say, okay, we already have an implementation of subtraction in the interpreter. So we're just going to call that one. And so essentially, subtract baseline does the exact same thing as the subtraction bytecode would do in the interpreter, but we just call it as a we call them native code stubs. So it's just a piece of code that we can call into. Now we can go through all of this. In the end, we have a native version of the same code that removed all the interpretation overhead, but still does exactly the same. And that's super easy to do, super quick, and we can do it liberally for almost all the functions that get called a couple of times. So that's only half the story. Actually, I hinted at it before. The minus bytecode can do lots of different things, right? It can do, well, minus is even not so bad, but if you think about addition, which can also mean string concatenation, but even minus, right? You might have, you might call to primitive. You might have to convert the values into something numeric. This might involve like calling user code, whatnot. So it's actually not. If we really want to do something optimal for the minus, we need to know more about what this piece of code is doing. And that's where type feedback comes into play. So I've put this here, which basically means while we're executing, we're also observing what the program is doing. We're learning things about the execution, and we're going to use that information in later tiers to produce more optimal code for you. So let's look at some more offending JavaScript code. I could use the class syntax, but the problem would essentially be the same. So, so what happens here is we create a new point object, and the point object has two properties. But this is actually only half the story. When we call this constructor, the object essentially starts empty. And then as we execute it, we slowly add property by property to this object. And you could have a more complicated constructor. You could have a constructor that maybe has a condition in it. Sometimes it adds the y, sometimes it doesn't. So from just looking at a constructor, we cannot know how this object actually will look like. So the only way to know how this object looks like is to actually observe what it does, what the constructor code does. But this would also mean that we would never know if two things are actually the same. Like, we could not rely that everything that is created by this constructor is the same object in the end. So how do we keep track of? There's a thing called hidden classes in the literature. In V8, it's called a map. And the map is basically the description of how an object looks like. And so this object, it will, like every object, it will start with the empty map. This is the map for objects with no properties. Then if I add a property, I will go to a different map. So I will change the map pointer of this object. And now the object has a map which says at offset 0, there's an x. And there is actually a thing called a map transition here, where I say, if you start with the empty map and then add the property x, you will get to this map. Then I'll do the same thing here. And now if you imagine that every object does that through the course of its lifetime, this essentially means that all the objects created by this well-behaved constructor function will end up with the same map. And now I have basically something shared, something that I can identify in the execution, where I know, if I see this map, I know how the object looks like. So what can I use this for? Let's say I have a function that loads x from such a point. Now, if I run this function the first time, I actually need to look at the object. I need to know, okay, what kind of properties does it have? Where do I find x? How do I access it? And well, you all know the property could also be a getter. It could be like, it's far from the only thing that could happen here that this is a data property. It could also be that the object doesn't have an x, and then I need to look at the prototype, whatnot. So what we do here is the first time we execute this, we'll do the full lookup. We'll figure out where is the x stored on that object. And then we'll cache that information. So every function has an attached feedback vector, and this is just some metadata that we keep track of while the function executes. And in this feedback vector, we can now store, okay, if you see this map, then you can access the property at offset 0. If you pass something else, then the object might look different, and we can add different entries to this metadata. So we can also say, if you see an object with this other map, then you should load the property from offset 1. And now you can actually see that it matters the order in which you define your properties. So if you change the order, then this is a different map, and we need a different accessor to get this property. In the end, we will have a list of all the objects that basically traversed through this point in source, and how they looked like, and where we found their properties. And now this information, I mean, it's already speeding up the interpretation, right? You can imagine the interpreter is now running faster because we don't need to do the lookup every time. When we get here, we already have the information. So the lookup, we only need to do it the first time. But that's not the most interesting part about this metadata. We can actually use it for the compilation tiers. So if now later we compile this function, the compiler will actually look at that information and it will specialize the code to the things that we have seen in the past. So with that, we get to the first optimizing compiler, which is maglev. So it's tier 3 in that hierarchy. And it fits in here. So it takes these, it takes that feedback that it gathered in earlier executions, and it will use it to produce specialized code. So how might that look like? Let's go back to our initial example here. And I'm not going to go through how exactly it works. It's not a compiler construction lecture. But here is, like, it might look something like this. And you can see a couple of things. We again have a graph representation of the code. We have explicit control flow, so we know which blocks of code are reachable depending on what happens. And we already have like some optimizations applied. For example, you can see the subtraction can be reused, so we don't actually need to compute it twice. We can figure that out in that graph. The other thing that is actually more interesting here is that we made a speculation now here. This code doesn't support any object anymore. It actually speculates that both of your arguments are float 64. And this is now something that we maybe have seen in the type feedback. We have seen like, okay, the arguments that you pass to these functions are only numbers. So we can actually specialize everything under the assumption that you will only call it with numbers. And of course, you can imagine this will now be a lot more efficient because we don't need this subtraction implementation that can do anything, but it's literally just a machine minus operation at this point. However, is this correct? I mean, you might just call the function with objects instead of numbers or with strings or whatnot. So this is actually a speculation that might turn out to be wrong. And so what we need to be able to say is at this point where we make the speculation, so I marked both of the speculations that we did with exclamation marks. At these points, we need to be prepared to basically undo our optimization, to give up on this optimization. And the way we do this is we have another side table next to our compiled code that will tell us how to reconstruct the state of the interpreter if it had run up to this point. So it's not that complicated to understand once you wrap your head around it. So basically, what we say here is if we would run up to this point, then the interpreter would be at bytecode 1, and the accumulator would contain the argument 1 to that function, because we already at this point we would have already executed that piece, like that instruction. That was the first load instruction, right? And as soon as we have this information, we basically know how to get back. So we can just say like, okay, exception, roughly speaking, let's stop the execution of this code. Let's reconstruct how the interpreter would look like, and then resume from there. So this is this red arrow. So whenever we have optimized code, we need to be prepared to go back. And yeah, finally, we have the last tier in our optimization pipeline. And here, I can share a bit what we're working on at the moment. So I'm actually not actively working on this. So most of the things that I present are either other people working on or people already did it 10 years ago. So this is, yeah, there's a long history of optimizations in that project. So TurboLev is a project that was sparked by the reasons behind that other blog post, which is called Leaving the Sea of Nodes. And basically what we observed is that our old last tier optimizer was basically sitting here. So it's parallel to maglev, it does the same thing, but better and with a completely different implementation. So if we zoom in, it looks a bit like this. We have the maglev frontend, which does all the optimizations, and then we have a maglev codegen, which emits native code, the backend of maglev. And then on the other side, we have turbofan, the optimizing compiler that uses the Sea of Node representation. And then it has a backend, which is called TurboShaft, which produces native code, which does instruction selection and peephole optimizations and whatnot. But actually, the front ends are doing almost exactly the same or doing very similar things. So the TurboLef idea is basically we take maglev, we make it in a sense configurable so it can do more or less optimizations, but it's the same compiler. And then we add a translation step to the existing TurboShaft backend. And by that, we are able to simplify the optimization pipeline quite a lot, because now both of our optimizing compilers will share the same front end. This is ongoing work. We might be able to experiment with it in the wild very soon-ish. Yeah, so this is the full architecture of V8 in one slide, focused on the compilers and the performance of the runtime, as it will be soon. Yeah, with that, I've already run through all my slides, and if you have more questions about the architecture or about V8 in general, I'm still around, happy to talk to people, and I guess we also still have time for questions.
In that complex architecture, the bug is complex and subtle to spot. So how to test this system is working? How to spot the bugs?
Yeah. This is actually a very good question, because like typically so there is for example, there's a conformance test suite called Test 262, which checks whether your implementation does what JavaScript is supposed to do. But to be honest, it almost never finds any issues in V8, because typically the issues are like, oh, if you first call this function with these arguments, and then you cause a garbage collection, and then the garbage collector moves this object there, and then you optimize it with this tier, then it will break. So it's very hard to get to the point where you actually trigger the bugs that we have. Nowadays we rely a lot on fuzzing, so coverage-based fuzzing, where we just throw random code at V8 and yeah, make sure it doesn't crash if you do that. Yeah, I think that's one answer, but the other answer is it's just an accumulation of lots of things which were wrong in the past and we now have in our test suite. But mostly it's black box testing. Yeah.
Thank you.
Thank you. And I would like to ask a question about that. So previously, TurboFun exists, right? And so the TurboFun optimize our code using single SSA.
SSA, yeah.
Single static alignment, so stuff like that. And so we skipped these types of optimization current. So next version of the
no. So maglev does all of that as well.
Maglev
so maglev is also an SSA graph. SSA basically means every value you cannot have a mutable assignment. So every value, if you have a variable in your SSA graph, then you only assign to it once. That's SSA, and almost all modern compilers use it.
I got it. いや、僕の質問はですね、前ターボファンでやっていた最適化、シングルスタティックアラインアサインメントかな、1回しかアサインしてないことを証明するための、行動っていうのもあったんですけど、最適化っていうのもあったんですけど、それをスキップしたのかって聞いたらそうではなくて、マークレブでやってるからやらなくて大丈夫なんだって言ってました。Thank you so much.